Welcome to our video on dark matter and dark energy, two of the universe's greatest mysteries. Dark matter is an invisible substance that does not emit light or energy but exerts gravitational effects on visible matter. It constitutes about 27% of the universe's mass and energy. Unlike ordinary matter, dark matter does not interact with electromagnetic forces, making it invisible. The existence of dark matter was first inferred from the observed rotation curves of galaxies. Galaxies spin faster than expected based on visible matter alone, suggesting additional unseen mass. Observations of galaxy clusters and cosmic microwave background radiation also support the presence of dark matter. Dark matter's gravitational influence helps hold galaxies and galaxy clusters together. Various theoretical particles are proposed as dark matter candidates, such as WIMPs, weakly interacting massive particles. Axions are another candidate, predicted by some theories to be very light and weakly interacting. Direct detection of dark matter remains elusive, with experiments ongoing to find it through its potential interactions. Dark energy is a mysterious force that is driving the accelerated expansion of the universe. It makes up approximately 68% of the universe's total energy content. The discovery of dark energy came from observations of distant supernovae, which revealed that the universe's expansion is accelerating. Before this discovery, it was believed that the expansion of the universe was slowing down due to gravity. Dark energy is thought to counteract the gravitational pull of matter and energy. The cosmological constant, introduced by Einstein, is one proposed explanation for dark energy. Another theory suggests dark energy could be a form of vacuum energy, known as quintessence. Quintessence posits that dark energy varies over time and space, unlike the cosmological constant. Dark energy affects the rate at which the universe expands and influences its ultimate fate. The total density of the universe is a critical factor in understanding its long-term behavior. The universe's fate depends on the balance between dark energy, dark matter, and ordinary matter. If dark energy remains constant, the universe may continue to expand at an accelerated rate indefinitely. If dark energy changes, it could alter the expansion rate or even lead to a collapse. Observations of galaxy clusters provide indirect evidence for dark energy by studying their distribution and movement. The large-scale structure of the universe is shaped by both dark matter and dark energy. Gravitational lensing, where light from distant objects is bent by massive objects, helps detect dark matter. Dark matter affects the motion of galaxies and galaxy clusters, influencing their formation and evolution. The presence of dark matter is crucial for understanding cosmic structure formation. Dark energy affects the geometry of space and the rate of cosmic expansion. The interplay between dark matter and dark energy is a subject of ongoing research. Theories about dark matter and dark energy challenge our understanding of fundamental physics. Experimental and observational efforts aim to reveal the nature of dark matter and dark energy. High-energy physics experiments, such as those conducted at the Large Hadron Collider, seek to discover dark matter particles. Space-based observatories, like the Hubble Space Telescope, provide crucial data on cosmic expansion and structure. The discovery of dark matter and dark energy has led to new insights into cosmology and astrophysics. Future missions and experiments aim to further unravel the mysteries of dark matter and dark energy. Understanding dark matter and dark energy could lead to breakthroughs in our knowledge of the universe. The study of dark matter involves investigating its effects on galaxy rotation and cosmic structure. Research into dark energy involves studying the expansion history of the universe and its future trajectory. The distribution of dark matter affects the formation of cosmic structures, such as galaxies and clusters. Dark energy's influence is seen in the accelerated rate of cosmic expansion observed in distant supernovae. Observations of the cosmic microwave background provide insights into the early universe and dark matter. Dark matter and dark energy are key components in the Standard Model of Cosmology. The lambda-CDM model, or lambda cold dark matter model, incorporates both dark matter and dark energy. The lambda-CDM model helps explain the observed distribution and behavior of galaxies and cosmic structures. The interplay between dark matter and dark energy shapes the overall evolution of the universe. Understanding dark energy requires analyzing large-scale surveys of the universe's structure and expansion. The study of dark matter involves exploring both its gravitational effects and potential interactions with other particles. Theoretical models of dark matter and dark energy help guide observational and experimental research. The search for dark matter includes efforts to detect it through its interactions with ordinary matter. The study of dark energy involves examining the effects of its presence on the universe's geometry. The cosmic web, the large-scale structure of the universe, is influenced by dark matter. Dark energy plays a key role in determining the rate of cosmic expansion and the universe's ultimate fate. Scientists use advanced simulations to model the effects of dark matter and dark energy on cosmic evolution. The study of dark matter includes searching for indirect evidence, such as gamma rays from dark matter annihilation. Research into dark energy involves analyzing the effects of its presence on the curvature and expansion of the universe. Understanding dark matter and dark energy requires a combination of theoretical and observational approaches. The interplay between dark matter and dark energy shapes our understanding of the universe's past and future. Research into dark matter includes exploring its role in the formation of cosmic structures. Dark energy's effects on cosmic expansion provide clues to its nature and role in the universe. The study of dark matter and dark energy involves a multidisciplinary approach, combining astrophysics, cosmology, and particle physics. The search for dark matter involves both ground-based and space-based experiments. The investigation of dark energy includes analyzing data from large-scale cosmic surveys and observations. Theories about dark matter and dark energy continue to evolve as new data and insights emerge. The study of dark matter includes exploring its potential interactions with other fundamental forces and particles. Dark energy's impact on the universe's expansion is a key focus of current cosmological research. Advances in computational modeling help simulate the effects of dark matter and dark energy on cosmic evolution. The quest to understand dark matter and dark energy drives much of modern astrophysical research. Understanding the nature of dark matter and dark energy is crucial for a comprehensive theory of the universe. The search for dark matter and dark energy involves collaboration across scientific disciplines and international research teams. Future discoveries in dark matter and dark energy research could revolutionize our understanding of the universe. The mysteries of dark matter and dark energy continue to captivate scientists and the public alike. The ongoing research aims to provide answers to fundamental questions about the universe's composition and fate. Dark matter and dark energy remain central to our quest for a complete understanding of the cosmos. Thank you for watching our video on dark matter and dark energy. We hope you found it enlightening. If you enjoyed this video, please like, share, and subscribe for more content about the universe and its mysteries. Stay tuned for more explorations into the cosmos, and keep your curiosity alive. See you in our next video, where we continue to unravel the wonders of the universe.